Thank you for the introduction. Ladies and gentlemen, as said, my speech will be about optimized NOx reduction technology for wide operation on non-road challenges. Shortly, first, what is Proventia, then discussion about key challenges in SCR, and then going to critical points in after-treatment system for optimum NOx reduction, including thermal management, urea mixing, flow characteristics, and SCR catalyst, and a quick summary. Proventia is a system integrator for engine, machine, and vehicle industries, high technology engineering, testing, and validation of our own products. We have been in the business for 23 years, and we are located in Finland, up north in Oulu, where we have our technology center and headquarters. Our business areas include emission control for OEM engine manufacturers, as well for vehicle and machine manufacturers. Engineering services supporting these functions of supply of components, and then we are also active in retrofit market, mainly for buses and trucks. We are also making our own thermal components for own products and also outside of Proventia Corporation, and then test solutions where we can test our own systems and also selling outside these test systems. For the after-treatment development drivers, at the moment they are real drive emissions, real world emissions, and in-use testing and monitoring, which will be coming also in the non-road sector. It needs efficient performance over wide temperature range, and ambient NO2 has been and will be a focus for certain areas, and therefore also as a tailpipe emission has to pay attention. And PEMS and OBD means that we have to do more precise onboard diagnostics for the systems, how they operate on the real conditions, so that there are no fault indicators of low efficiencies. Fuel economy and cost efficiency, they are a topic, and it has been discussed already in the morning time that possible EGR dropout leads to increased NOx emissions, but also gives cost benefit for the machine and engine. For the non-road side, there's always a limited space available for after-treatment, and that requires compact design of complete after-treatment. Then for the SCR development, one of the challenges is that it has to operate over wide temperature window. Full load conditions is one normal parameter for engine testing, and there the high mass flow and high NOx must be handled with the precise controlling of ammonia and excellent ammonia distribution without any slipping of ammonia. On the other hand, low load and low ambient temperature conditions can be very similar than city traffic in on-road applications. Now, as stage 5 will have DPF, some manufacturers will have to add DPF. It gives temperature delay from the cold start, and therefore also higher efficiency target for the SCR NOx reduction is required. In generally, high NOx reduction target is set. That means that more urea has to be injected at low temperatures, and then there is a risk for wall wetting inside exhaust pipes. Hopefully, all the urea dosed in the system will be converted into ammonia and utilized in the SCR reactions. And then SCR catalyst chemistry also has to cope with high NOx reduction targets. The limited space which is available in engine compartments means that shorter mixing lengths for urea has to be applied. Urea evaporation and decomposition into ammonia is even more critical. and again the wall wetting and deposit formation is more difficult to control. This is a map of an engine for certain mass flows as well temperature ranges, and the low temperature side is critical for evaporation, but on the other hand also high temperature point needs precise ammonia distribution over the catalyst. And not only the temperature but also the mass flow. The same engine can have very low mass flow conditions or high mass flow conditions, and at the low mass flow end it becomes critical that how the evaporation takes place, and on the high mass flow side it could be back pressure which is limiting the design of the after-treatment system. So the dosing control has to be optimized both for mass flow and for temperature window, and both cases low and high ends are critical. For the after-treatment system, it is a game of different parameters including engine control, dosing calibration, and that is mainly responsibility of the engine and what happens in the engine. The other parameters what can be affected by exhaust line design is thermal management, urea mixing, flow characteristics, and SCR catalyst. So we can affect from engine after-treatment manufacturing point of view what happens in terms of temperature in the system, urea mixing, flow characteristics, and choose the right SCR catalyst. First, for the thermal management, it's possible and recommended to have insulation as a tool for thermal management. Multi-layer insulation so that there is a insulation wool as a first component next to the exhaust component, and then a skin of stainless steel is very suitable solution. This can be fit on tight engine compartments and improves SCR performance, and also the heat loss is less from engine to after treatment. It can improve also fuel economy in case that there are heating functions in the engine. In tight space claims of non-road applications, surface temperature is also in control, which gives possibility to build these compact machines. Here is an example of just a straight, more or less a straight pipe, typical for non-road application, and it has been tested, demonstrated with different thicknesses of insulations, and we can see that even any insulation, we are saving about 8 degrees C in temperature from turbo to after treatment. So less thermal loss in that distance. And this temperature loss is greater when low mass flow of engine is used. So the benefit for the insulation is really on the low duty points of the engine. And the outside skin temperature also keeps low. So in this case, having different kind of load points, we can see that the exhaust pipe temperature is up to 350, 370 degrees C, and with thick insulation we are below 100 degrees C, and this is significant difference. So, and also a thin layer of insulation provides pretty good skin temperatures. Then for the urea mixer, efficient urea mixer like Proventia Super Tornado, we can inject more urea solution at short exhaust pipes and challenging conditions. We can have even ammonia distribution at low and high speed, so both ends of mass flow. And inside the pipe we have turbulence, providing faster evaporation of water from urea, and ammonia is well available for the SCR reactions. In the mixer we have two swirls in the center of the pipe, and then the other on the outer side of the pipe. With these swirls, the water gets evaporated faster from the urea droplets, and the second flow, which is here on the outside of the pipe, is protecting the outer surface and the cold areas of exhaust pipe from wall wetting. We can have bends directly after the mixer and really short distances. Here we have an example of how much we can dose urea. These orange bars here present nominal dosing range, so how much is the alpha or desired amount of AdBlue to be dosed, and the blue bars present how much of safety margin or optimization margin there is available with this mixer. So this area and this difference, this margin can be utilized for changing the engine out NOx to higher level, or it can be used to allow overdosing of the SCR calibration, so filling up ammonia storage capacity in the SCR if required, or it can be modified, or it can be utilized for going to lower temperatures. Few examples on different mass flow conditions, all about on the same temperature of 180 degrees C, and we can see that with this system we can start the dosing at 180 degrees C or even colder, and with also quite wide mass flow range in this low end side. The engine was a bigger engine, 200 kilowatt, maximum of about 1300 kilos per hour, so this really represents the low end of mass flow condition. On the high end, we don't typically see the problem of deposit formation. We see more on the back pressure side the challenges for the mixer or distribution on the catalyst. And previous slides, the mixers, they were all clean, but this is how it looks like when there is a small amount of deposit. And we are doing the deposit testing by running the test for 30 minutes, and by doing this we can see already visual marks where the deposit is starting. If we would continue this by up to 3 hours, we would partly block the mixer and really see a difference on flow characteristics in the exhaust system. This kind of deposit is not critical if it takes place for a short duration, but it has to be followed by higher temperature and or lower dosing amount. Then there are also differences on different mixers. here is apple-to-apple comparison to two different mixers, injector A and B. A is having a wider cone and B is having a more narrow cone of the spray. And with the injector A, we can inject about 600 grams per hour, and injector B about 900 grams per hour, and the result is the same, that no deposit is visible on the system. So the injector also makes pretty much difference how much it is possible to dose and have engine baseline NOx values. And this is again how it looks like when there is deposit visible in the pipe. Then on the SCR, ammonia uniformity index is directly linked to SCR efficiency. We are using CFD as a tool for the base design, and then we have to do also experimental measures to verify that the CFD was correct. And when we have high ammonia uniformity index, meaning that close to 0.99, we can see that the ammonia slip is on a minimum level. Here we have one from high mass flow conditions reference point, seeing that on the left-hand side it is from simulation, and the right side is from experimental verification to see that how much it really was. And we have a nice match between these two values. The verification of ammonia distribution is done with this kind of scanning device, that we scan the whole outlet side of SCR and measure emissions, basically NH3 and NOx from the outlet side. By scanning this outlet side, we can see the distribution, how efficient the SCR has been on which part, meaning basically that how much of ammonia is available on different parts. This minor difference also on the ammonia uniformity is visible also for NOx sensors. So if we are not taking the NOx sensor reading for the OBD from average value, we are getting wrong signal, either too high or too low NOx reading. And therefore we have to also see that the NOx sensor, what we are placing in the system, is on representative point of the flow. And we are checking this by having a test NOx sensor, as well the reference NOx sensors down the line, where the system is fully mixed and gives average value for the NOx sensor. Then for the SCR, as we all know, SCR efficiency plays a big role in the system, but our point of view is that first all these previous points, thermal management, distribution of ammonia, has to take care before going into SCR. If those previous points are on good level, it's possible to minimize also SCR volume when all the other parameters are high, on high level. Substrates and coating, they are partly also depending on what kind of overall strategy is chosen by engine manufacturer, how much of active regeneration is taking place, and that is more dominant factor than the other parameters here. So, as a summary, integrated insulation gives a nice tool to save thermal energy for the after treatment. Then good mixing of the ammonia and distribute that well on the SCR, and a good catalyst and then most likely you will meet your targets. Thank you.
Thank you. Thank you, Arno. Do we have any immediate questions from the floor? Maybe I can start off then. Arno, you mentioned that you're looking at engines without EGR. Now, typically, these are engines which will be about twice the level of NOx than an EGR engine. But it is also the case that taking EGR off also makes the exhaust temperature hotter, doesn't it? Because you're no longer cooling that recirculated gas. How does that then impact your overall amount of dose when you're comparing like-to-like temperatures? What do you find on that?
Most likely it is that if we are leaving out the EGR away, the temperature difference is 5 to 10 degrees or 20 degrees C. So that doesn't play that much of role. Of course, if it's on the critical area between 200 and 250, then it makes difference. But definitely the dosing amounts when leaving the EGR away at the low temperature and low mass flow situation is the critical one.
So really you're saying it is quite justifiable to say no EGR engines are much, much harder to achieve deposit free. Yeah.
With some systems, yes.
Yeah. Okay. Maybe it is more complicated. Okay. Thank you. Anything from the floor? Please.
Ralph Miller from MTU. Regarding urea deposits, you mentioned that the test duration was 30 minutes, whereas at 3 hours testing there may occur some blocking of the mixer. Is 3 hours duration relevant for some of your applications?
We have, in the early days, we developed a cycle where 1 day corresponded about 500 hours in the field test. So we did a little bit of overdosing. From there we have been able to squeeze down the test time to 30 minutes. And the pass or fail criteria is that if it's fully clean at 30 minutes, it remains fully clean for end of the life, if it just remains on the same conditions. But if there are any deposits after 30 minutes, we do see a risk. And then the level of risk is depending on what engine point we are running. So some engine points are not that critical if we see a little bit of deposit. And also the location. So if we see location further down on the exhaust line, it's not that critical because the urea has already formatted different characteristics and lost main portion of the water by that.
Okay, thank you.